Hello, I'm Ted Pyne, and I'm going to be talking about pseudorandom generators for unbounded-width permutation branching programs. And this is joint work with William Hoza and Salil Vadhan. The pseudorandom object we will be considering is the pseudorandom generator. A function gen on 0 1 to the s to 0 1 to the n is an epsilon PRG for a class of functions f on 0 1 to the n to 0 1 if for all little f in f, the probability that f returns 1 or accepts over truly random input is within epsilon of the probability that f accepts given the output of the PRG. Sometimes we'll also say that in this case, gen epsilon fools the class f. The computational model we consider is that of ordered branching programs, parameterized by width and length. A branching program B has n time steps, where the transition function at each time step as defined as a function between the state in W and the next bit of input in 0, 1. This is a non-uniform model motivated by the derandomization of space-bounded computation. A space S algorithm using R random bits can be represented as an ordered branching program of width W equals 2 to the S, where intuitively each state refers to some memory configuration, and each time step refers to reading the corresponding random bit. For instance, we have a width equals 3, length equals 3 branching program here. And here we note that there's an alternative perspective where we can view a branching program of length n and width w as an n+1 layer graph where each layer has w vertices, and the transition functions correspond to edges between layers. Here, we use red edges to represent the transition upon reading 1, and gray to represent the transition upon reading 0. And we note that we also specify an initial start vertex and a final accept vertex. Just to make this more concrete, here we have the same ordered branching program, and we show how to evaluate it over some input. So given the input 0, 1, 1, we transition between states according to the transition rules, where note here that the transition rules or the relevant graphs are allowed to be different between each layer. And so we read the input bits once and in order, which is why these are ordered read once branching programs. And in this case, we reach the accept vertex after reading the input. And so we say that the branching program evaluates to 1 on the input 0, 1, 1. An explicit pseudorandom generator for branching programs of width polynomial in n and length n with seed length order log n suffices to derandomize space-bounded computation in that it implies BPL equals L. Via the probabilistic method, a random function, g, on 0, 1 to the order log n to 0, 1 to the n, is a PRG for polynomial width branching programs with high probability. The best known explicit PRG, however, for general branching programs by Nissan in 92, has seed length order log n over epsilon, which is a quadratic factor away from desired. Here, we have the fact that the probabilistic method provides the best possible seed length, and we desire to create explicit constructions that are as good as a random function. However, given the lack of progress on the general model, attention is turned to restricted classes of branching programs. When we restrict to subclasses of branching programs, we place conditions on the transition functions. For a regular branching program, we require the transition function at each layer to define a regular graph. Since the transition function is already 2 out regular, this in practice requires that each state has 2 incoming edges. Moreover, for a permutation branching program, we require that for every time step and for every input bit, the transition function upon reading that input bit at that time forms a permutation on the states W. The width 2, length 1 regular branching program below is not a permutation branching program because, as we can see, the red edges do not form a permutation on the states. In fact, neither do the gray. Our focus is on permutation branching programs of arbitrary width with a single accept vertex. This is an unusual model because distinguishing functions can have exponential description size, since the width can be up to 2 to the n, and arbitrary space usage. Restricting to a single accept vertex is essential, since otherwise this model can compute any function. Day gives a PRG for this model with seed length order log n over epsilon, but that was not the main focus of his paper, which is in fact focused on constant width permutation branching programs. The best known PRG for permutation branching programs of constant width have seed length log n log 1 over epsilon. We now present our three main results. The first is that the Impagliazzo-Nissan-Wigderson INW PRG epsilon fools arbitrary width permutation branching programs with seed length order log n log 1 over epsilon plus log n log n. Our second theorem is that a random function g with seed length little o of n fails to be PRG for arbitrary width permutation branching programs with high probability. This is in direct contrast to the polynomial width case, where a random function already achieves the optimal seed length, where here we give an explicit PRG that has seed length exponentially shorter than that obtainable via the probabilistic method. The final theorem is that any epsilon PRG for arbitrary width permutation branching programs has seed length omega of log n log 1 over epsilon. This is also interesting because we have an explicit lower bound forcing a multiplicative dependence on log 1 over epsilon, whereas for the polynomial width case, we only have additive lower bounds of the form log n plus log 1 over epsilon. In order to prove the first result, we first need to define some notation. Given a permutation branching program, B, of length n and width w, the execution graph of B, which we denote G, has n plus 1 layers, each with w vertices corresponding to the states. We can make this regular by adding the identity matchings from layer n plus 1 to layer 1, as shown below. We take some permutation branching program and add the identity between the final and initial layer. Moreover, for permutation branching programs, this graph is consistently labeled. The incoming edges at each vertex have distinct labels, and this is important for a correspondence which we'll use later. We can then reason about powers of this execution graph. Given a permutation branching program B with execution graph G, we can define the random walk matrix of transition I to be W sub I. Then the random walk matrix of G has the form of a block matrix where the block in column I and row I plus 1 corresponds to the transition between layer I and layer I plus 1. Then, if we take the Lth power of this random walk matrix, or the Lth power of the corresponding graph, the I plus L block corresponds to the random walk matrix for layers I plus 1, I plus L of the branching program. And so we have the fact that an edge v comma w in G to the L corresponds to a walk in 0, 1 to the L from V in layer I that reaches W in layer I plus L. Essentially, edges in high powers of this correspond to walks over the input 0, 1 to the L that go from a particular vertex in one state to a different vertex in the layer corresponding to the correct length. Our goal is to select a sparse set of these walks that still approximates the true power. Recall that there's an edge between state V in layer I and state W in layer I plus L in G of L if there's a walk in 0, 1 to the L from V that reaches W. The graph B bracket gen induced by a PRG on 0, 1 to the S to 0, 1 to the L is the subgraph where we have an edge from V to W if there is a particular seed for the PRG such that the generator output on that seed, gen of sigma in 0, 1 to the L, when used as the sequence of bits from V reaches W. For instance, if gen is the trivial PRG that represents the identity map on 0, 1 to the L, then the graph induced by the PRG is simply the Lth power of the execution graph. Our goal is to create PRGs of length n such that the graph induced by the PRG approximates G to the n. In fact, we can see from the block matrix structure on the previous slide that if we manage to approximate the nth power of this, there will be a block corresponding to W1 times W2 Wn. And so we will have managed to approximate the products of the random walk matrices of the transition functions and thus approximate the acceptance probability of the branching program over truly random input. Furthermore, we have a useful correspondence between powering these graphs and concatenation of PRGs. Letting B be a branching program and gen a PRG, then the graph induced by gen squared is equal to the graph induced by the concatenation of gen with itself. Intuitively, on the left side, squaring this graph corresponds to combining all possible walks over the output of gen with a second independent walk over the output of gen, but this is precisely what the right side is. With this correspondence, it may motivate our definition of the INW generator. The INW generator is recursively defined using a family of auxiliary graphs, H sub I, where each vertex in H sub I plus 1 corresponds to a seed of the ith INW generator. The base case, the INW sub 0 generator, is the trivial PRG that outputs its 1-bit input. Rather than defining INW sub I plus 1 as a concatenation of two independent INW sub I generators, which would double the seed length, we sparsify by restricting to pairs of seeds, x and y, that are neighbors in H sub I plus 1. For H sub I plus 1, the complete graph on the seeds, this is equivalent to using independent seeds, so we wish to use much sparser graphs that still provide a high-quality approximation. Just as a notation, note, we write lambda of h for a regular graph h to denote its second largest eigenvalue in absolute value. And we're now prepared to state our main result. The INW pseudorandom generator constructed with auxiliary graphs h sub I with lambda of h sub I order epsilon over log n is an epsilon PRG for permutation branching programs of arbitrary width. We note here that the required spectral gap of h sub I only depends on epsilon and the logarithm of the length. It has no dependence on the width of the PRG, and only a logarithmic dependence on the length of the power that we wish to estimate. The proof overview is we wish to show that the graph induced by INW I plus 1 approximates the graph induced by the concatenation of INW I on any permutation branching program B using a connection to the derandomized square and notions from Ahmadinejad, Kellner, Murtaugh, Peebles, Sidford, and Vadhan. We now introduce some more details of this proof. The derandomized square of G with respect to H uses H to correlate two steps in G, and thus select a pseudorandom subset of walks in G squared. Intuitively, if we think of taking a step in G squared as taking two independent steps in G, rather than including all possible combinations, we only include the combinations that are neighbors in H. This may seem similar to the IW generator, and in fact, the construction is essentially identical. We have this lemma from Rosenman and Vadhan, such that for any permutation branching program B, where the permutation condition is important because otherwise these graphs are not necessarily consistently labeled, we have that the graph induced by the ith INW generator on B, derandomized squared with the I plus first auxiliary graph, is equal to the graph induced by the I plus first INW generator on B. And so now we can work with the derandomized square of consistently labeled graphs. Our next goal is to show that repeatedly derandomized squaring a graph, L times, approximates G to the 2 to the L. And so by this correspondence, this will show that the log nth INW generator, the graph induced by the log nth INW generator, approximates the nth power of the graph induced by the trivial INW sub 0 generator. But this is precisely the random walk matrix of the PRG, raised to the nth power. To do so, AKM et al. Define a notion of unit circle approximation between matrices. For concreteness, we can think of A and C as the random walk matrices of regular digraphs. We say that A is an epsilon unit circle approximation of C if the following inequality holds. We abuse notation and say that graphs unit circle approximate each other when their random walk matrices do. So we claim that if B is some permutation branching program with execution graph G, then if the graph induced by gen is an epsilon unit circle approximation of the nth power of G, then gen epsilon fools B. For the proof, we take these test vectors, x and y, in the definition to be the indicator vectors for the start and end vertices of the PRG, where the start vertex is in layer 1 and the end vertex is in layer n plus 1. Then the left-hand side of the unit circle approximation definition, we can see that these characteristic vectors essentially cut out the start comma end entry of this matrix, of these matrices. And so their difference is precisely the statement of what epsilon fooling is. On the right-hand side, we have the epsilon over 2 multiplied by the norm of both of these vectors, which are both 1, minus this complex form, which requires that unit circle approximation exactly preserve all eigenspaces with complex magnitude 1. But in this case, we use the trivial inequality where we drop this negative term and simply get on the right-hand side epsilon. Akam et al. Use the derandomized square and preconditioned Richardson iteration to give nearly logarithmic space algorithms for high precision estimates of random walk probabilities on Eulerian graphs. In order to do so, they prove two important theorems that we use. First, the derandomized squaring yields a unit circle approximation of the true square. Here we note that the quality of unit circle approximation depends only on the magnitude of the second eigenvalue of the auxiliary graph and does not depend on the size of the main graph being derandomized squared. This is important because the size of the execution graph of a permutation branching program of arbitrary width can be up to 2 to the n times n. And so a linear or even logarithmic dependence on the size of the graph being derandomized squared would not give a non-trivial PRG. Second, they show that unit circle approximation is preserved under arbitrary powers. And we show a quasi-triangle inequality for unit circle approximation. From these, we can show the main tool for the upper bound. Let G be some regular digraph, and G2 to the k tilde, the graph obtained by taking k derandomized squares with some auxiliary graph family h sub I, with lambda of h sub I is less than epsilon over 8k. Then, G of 2 to the k tilde is an epsilon unit circle approximation of G of 2 to the k. Note that here, we take loss linear in the number of derandomized squares. Thus, we require the spectral gap to be bounded by epsilon over 8k, but this is loss logarithmic in the ultimate power, since each derandomized square doubles the length of walks under consideration. Now we have the ingredients to prove the main theorem. Let B be any permutation branching program of length n equals 2 to the k, and let its execution graph be G. Then let G2 to the k tilde be the kth derandomized square of G with respect to the expander family on the previous slide. First, we have that G2 to the k tilde is an epsilon unit circle approximation of G of 2 to the k. Second, we have that G of 2 to the k tilde is equal to the graph induced by the kth IW generator on B, by the result of Rosenman and Vadhan. Therefore, we have that the INW sub k generator, the graph induced by it, is an epsilon unit circle approximation of G of 2 to the k. Then, by choosing test vectors, as in claim 4.6, we have that INW sub k epsilon fools B. Since B was arbitrary, and this correspondence of Rosenman and Vadhan does not depend on the branching program B, we conclude. We now move to our second result, that of the failure of a random function to be a good PRG. Precisely, a random function with seed length little of n fails to be a PRG for arbitrary width permutation branching programs with probability 1 minus little of 1. This means, in contrast to the polynomial width case, our explicit construction is vastly better than that obtained via a random function. The key to this result is that exponential width permutation branching programs can compute doubly exponentially many functions. Here we give a specific set of test functions that we'll use to show that a random function fails. The key idea is that unbounded width permutation branching programs can check permutations. Let tau be a permutation on 0, 1 to the s. Then there's a length 2s with 2 to the s permutation branching program b sub tau, such that b sub tau accepts on x comma y if and only if tau of x is equal to y. We show this by explicitly constructing such a permutation branching program. We identify the state of the branching program with 0, 1 to the s, and let E1 through ES be the standard basis vectors. We then give this transition function, which can be checked to define a permutation branching program because the transition function applied to itself is the identity map on states. On input x comma y, for the first S layers, we XOR x into the state of the branching program. So at layer I, we XOR the ith bit of x into the state. At layer S plus I, in the second half of the branching program, we apply tau and then XOR the ith bit of y onto the state. Therefore, B sub tau on x comma y terminates at the state tau inverse of tau of x XOR y. Then by choosing tau inverse of 0 to be the accept vertex, we see that this branching program accepts if and only if tau of x XOR y is equal to 0, as desired. Now let G be a random function, 0 1 to the s to 0 1 to the n, with s little o of n. Then with probability 1 minus little of 1 via simple union bound, the n over 2 bit prefix, L of sigma, the first n over 2 bits of G's output on sigma, and suffix, R of sigma, the second n over 2 bits, are injective. In effect, the second half of the PRG's output is determined by the first half with probability 1 minus little of 1. But then there is a permutation pi on 0 1 to the n over 2, such that pi applied to L of sigma is equal to R of sigma for all seeds sigma. Then let B sub pi be the permutation branching program testing pi, as guaranteed to exist by the previous lemma. We can see that B sub pi applied to the output G of sigma is equal to 1 for all seed sigma, in that the permutation branching program accepts on all outputs of the random function. However, B sub pi accepts a random n-bit string with probability exponentially small in n. So the gap between acceptance probabilities over PRG output and truly random output is almost as large as possible. And so G fails to be a PRG. It's worth remarking here that the reason the INW generator manages to pass such tests is that it injects new randomness at every half. In effect, if the output of a function is the output of the second half of a function is highly predictable given the first half, we show that there is a permutation branching program that manages to accept over this function with a high probability, where over truly random output, it would be vanishingly small. We can use a similar idea to show an unconditional lower bound of omega of log n log 1 over epsilon for any epsilon PRG for arbitrary width permutation branching programs. The proof idea is that if one half of the PRG output is somewhat predictable given the other, then there's a permutation tester branching program that accepts PRG outputs with noticeable probability. The key lemma is for jointly distributed random variables, x and y, each over some universe n. There's a permutation tau on n that satisfies the probability that tau applied to x is equal to y is lower bounded by 2 to the negative conditional entropy of x given y plus conditional entropy of y given x. The proof idea comes from the fractional Koning-Evergavari theorem. And essentially what we wish to do is we wish to find a heavy weight matching on the distribution of the random variables x and y. We now give a sketch of how we move from this lemma to the lower bound. Let gen, 0 1 to the s to 0 1 to the n, be an epsilon PRG for the model, and x and y the random variables of the first and second half of the output. The first n over 2 bits of n and the final n over 2 bits, the first n over 2 bits of gen and the final n over 2 bits of gen must both epsilon full permutation branching programs of length n over 2, since permutation branching programs can ignore sections of their input. By lemma 6.4, we have an omega of log 1 over epsilon lower bound on the sum of the conditional entropies of x given y and y given x. Then we can decompose the joint entropy 2 different ways, using this basic, using the chain rule. And then we have an inductive argument which completes the proof, where we show a lower bound on h of x and h of y, and a lower bound on the conditional entropies via the lemma. So in conclusion, we've explored 3 aspects of pseudorandomness for permutation branching programs of arbitrary width with a single accept vertex. First, there is an explicit PRG for the model with seed length nearly linear in log n. Second, a random function with seed length little of n fails to be a PRG for the model with high probability, showing that there is an exponential gap between explicit constructions and random constructions, but in this case, the explicit constructions win. Finally, any epsilon PRG for arbitrary width permutation branching programs has seed length omega of log n times log 1 over epsilon, in contrast to the polynomial width case. We conclude with some open questions. The first is removing the log n term in the generator seed length. This would imply asymptotically optimal PRGs for arbitrary width permutation branching programs, and would also constitute the best known PRG for permutation branching programs of constant width via a simple union bound over the accept states. The second is the existence or non-existence of PRGs for regular branching programs of unbounded width, where no non-trivial PRG is known. And the third is connecting back some of the ideas to space-bounded derandomization. Thank you.